good afternoon. Just a couple of quick housekeeping points. There's normally a class comes in here straight at 1 o'clock. So you can do a desperate to ask Meha questions at the end of this particular seminar. She's going to have to go with the doctoral program actually to 3:21 exactly at 1, so we'll leave on time. And I'll let her referee questions. But if you want to grab time to meet with Meha again, she's around for the next 2 days. And at 4 o'clock tomorrow, in 319, she has coffee scheduled for all of our master students. So you should feel free to go. And doctoral students can also go at 4 o'clock tomorrow as well. Everybody, all students are welcome. If you're faculty, you're not welcome. I was going to read your title, but it's up there. So Meha is an assistant professor at the University of Michigan. She's been here since 2016, and came by way of a PhD at Columbia, and then a postdoc at Stanford. Oh, can you not hear me? I'm going to keep shouting. She's got more than 20 papers published already, with numerous others submitted, and brought in well over 1.5 million in grant funding already. What's particularly exciting for me, however, is Meha's scholarship. So this has already been recognized. If you go and look at her papers, the editorial boards of the various journals that she's publishing in has highlighted her manuscripts for various reasons, including being among the top 10 papers, for example, in adaptation research. The reason for this is that she essentially, with her own scholarship, does the, if you like, the pinnacle that we want to achieve at FES. She bridges both natural and social science, right? I wish that most of us could say we do that. So she combines, very specifically, remote sensing and geospatial analyses with household level and census data sets, with the focus on understanding household level farmer decision making and behavior across large spatial and temporal scales. At Michigan, she teaches natural resource statistics, and her focus in that class is really teaching the correct statistical approaches to address the right applied issue that you have. I'm not going to say any more because I don't want to take up her time. I'm just going to let her start. We're very delighted to have you here at FES. Thanks.
Thanks so much for that wonderful introduction. So, environmental change, including climate change and natural resource degradation, is negatively impacting agricultural production across the globe. At the same time, demand for food is increasing due to growing populations and changing diets. And because of this, studies estimate that agricultural production will have to increase by up to 75% over the coming decades to meet global food security, which ensures that all people will have access to a sufficient quantity of affordable and nutritious food. What my research group examines, and what I'll present today, is work on how farmers may be able to adapt or change their cropping practices to reduce the negative impacts of environmental change on production. I also look at how farmers may be able to sustainably intensify their agriculture or increase production while using limited, scarce natural resources. By doing this, my group and I identify potential solutions and interventions that may enhance agricultural production in the face of environmental change. So to date, most of our work has taken place in India, and that's because this is one of the hotspots for food security across the globe. India is one nation that is expected to face negative shocks to yield due to warming temperatures, and this is particularly true for staple crops like wheat. At the same time, monsoon rainfall patterns are changing with increased break periods and more intense rainfall events. And at the same time, the natural resources on which agriculture depends, like groundwater, are becoming rapidly degraded across the country. So India is the largest consumer of groundwater worldwide, and groundwater provides 60% of India's irrigation, yet over 50% of wells are declining across the country. At the same time, demand for food will increase, so India's population is projected to keep on growing, and India is projected to become the most populous nation by 2030, with over 1.5 billion people. So these potential negative losses to production aren't only a matter of food security, but they're also a matter of household welfare, given that agriculture is a primary livelihood for over 50% of India's population, which is about 8% of the global population. So what can we do? how can we ensure food security in the face of environmental change? So there are many different aspects of food security, but what I focus on with my lab group is identifying ways that we'll be able to increase production in the face of environmental change. And we do this by focusing on two specific strategies. The first is identifying ways that farmers may be able to adapt to reduce the negative impacts of environmental change on production. And what I mean by this is, say that scenarios estimate that warming temperatures will decrease wheat yields by 10% over the next 50 years. In reality, if farmers can actually change their practices, so say switch to more heat-tolerant wheat varieties, they might be able to reduce this loss to only 5%. And this suggests that adaptation could reduce yield losses from environmental change by 50%. So with my work, I not only examine what's called autonomous adaptation, or that's adaptation that farmers are already doing in response to environmental change, I also think about what are some additional strategies that could be further promoted to help farmers adapt even more into the future. The second mechanism that we focus on to think about ways to increase food production is thinking of ways that we can promote sustainable intensification management practices to close existing yield gaps. So what the idea of a yield gap is it's the difference between the average yield on a farmer's field currently and the potential yield that that farmer could achieve if he or she adopted ideal management practices. So what we try to do is we try to identify what are these management strategies that farmers can adopt to close these existing yield gaps. To do this work, I take a strongly interdisciplinary and systems approach to define the impacts of environmental change, potential solutions, and also the most effective ways to deploy interventions. And I'll walk you through this conceptual framework that drives my work by going over the four main research questions in our lab group. The first is understanding what are the projected impacts of environmental change on agricultural production. So in the case of warming temperatures, how much will warming actually reduce wheat yields? The second question is the impacts of environmental change are mediated by the decisions that farmers make, by their actual cropping strategies. So what we want to do is identify what are some potential management factors that farmers can adopt to reduce the negative impacts of environmental change or to close yield gaps. The third question that I ask is trying to understand what are the social, economic, perceptual, and biophysical factors that influence these crop management decisions. And this is because some of my previous work has shown that even if farmers in the same community experience the same weather shock or the same long-term environmental change, farmers have different responses and they will be impacted differentially. So we do a lot of work to try to understand this heterogeneity it impacts and this heterogeneity in decision making. And then finally, I work to understand whether we can use this information to design more effective interventions to actually increase production moving forward. So to do this work, I use a mixed methods approach where I combine satellite image analysis or remote sensing with household surveys on the ground to identify how farmers may be able to enhance production at large spatiotemporal scales. And the reason that I use satellite image analysis or remote sensing is because most studies that to date have asked questions about increasing agricultural production, the way they do this is by relying on typically used census statistics. So these are typically statistics provided by governments at an administrative unit. So in India, for example, a lot of the agricultural production data is available at the district scale, which is the equivalent to a county here in the US. And this is a map showing district level boundaries in black across all of India. But what I argue is that by doing analyses at this coarse resolution, you don't get to understand the heterogeneity and the impacts within a given region. So in order to do that, I derive novel satellite data sets on both agricultural management decisions and also production. And this allows me to get estimates of these types of data at very high spatial resolutions, so typically ranging from 30 meters to 250 meters, which you can already see is much better than these coarse level district census data sets. And I'm also able to do this at large spatiotemporal scales because satellite data are available across the globe and for decades. So these are just examples of some of the cropped area and crop management products that I've created. And what I'll show through my talk is that data at these finer spatial resolutions reveal important heterogeneity that's typically masked by using readily available coarse data sets. So this is an example map of a cropped area that I produced across all of India, and this data product is at a 1 by 1 kilometer resolution from 2000 to the present. So you can already see that there's much more fine-scale variation that you can get from these type of data than these coarse-level statistics. I also do household survey data within the footprint of the area where I do the remote sensing analyses. And this is because household survey data allow me to understand heterogeneous decision-making and the different factors that are explaining why certain farmers adopt one strategy over another. Broadly, I'm looking at the impacts of multiple environmental changes on agricultural production. I'm looking at warming temperatures, groundwater depletion, and changing rainfall patterns. But for today's talk, I'm only going to focus on my work focusing on the effects of warming temperatures on agricultural production in India. And specifically, I'm looking at wheat systems and figuring out ways that we can adapt wheat systems in India to warming temperatures. The reason that I'm looking at wheat is because wheat is one of the crops that is expected to be most negatively impacted by warming temperatures. So studies have shown that in India, wheat yields have already declined by 5%, and they're projected to decline by up to 15 to 20% more over the coming decades due to warming temperatures. This is of concern because India is the second largest producer of wheat globally. Most of the wheat is produced in this region, the Indo-Gangetic Plains, highlighted here in red, and much of my work takes place in this region. And you can imagine that large losses in wheat are going to have large impacts on household food security because wheat makes up 20% of household calories in a given Indian diet, both from traditional and not so traditional sources. So in order to do this work, I'm closely working with collaborators on the ground. And specifically, I'm working with CIMMYT, which is an international institute headquartered in Mexico that's trying to find ways to increase grain production across the globe. And they have a regional office based in India called CISA. And this is a picture of two of my closest collaborators from this organization of us in the field in India. Balinder Singh is an agronomist, and Amit Srivastava is a GIS specialist. So I'm going to highlight 3 specific projects that I've worked on with my lab that will highlight the benefits of taking this systems and interdisciplinary approach. So the first project identifies what are some management strategies that can close yield gaps and reduce the negative impacts of environmental change, specifically warming temperature, on wheat yields. And this focuses on, and highlighted in red, the part of the diagram that I'm working with. So to do this work, I use satellite data to quantify yield gaps. So specifically what I did, I'm not going into the details of any of my remote sensing work, but I would be more than happy to speak with anyone about this after the talk. But what we did was I created a map at 30-meter resolution across all of northern India on wheat yields from 2000 to 2015. And you can see that when we correlate this or validate this using census-level statistics, we're doing a pretty good job. These are pretty good Rs for remote sensing, especially because we didn't use any ground data for calibration. And what I argue and what I'm going to show through this project is that satellite data are really important to use because, one, they allow us to more accurately estimate the magnitude or the size of yield gaps. And second, they allow us to better understand what the management factors are that can actually close these yield gaps. So typical work that does yield gap analysis, as you guys remember, this is the difference between current farmers' yields and the potential that they could receive in yields if they adopted ideal management strategies. The way that most studies typically define what this potential yield is they'll use crop model simulations. So crop models are mathematical simulations that will estimate crop growth and yield based on a variety of inputted weather and management factors. But what I argue is that these types of models do not account for realistic biophysical and socioeconomic constraints to production. So for example, in the model, you might say that the farmer will irrigate at full capacity, but in reality on the ground, this might not be possible because there might not be that irrigation infrastructure in order to do so. So instead, what I use as a measure of this potential yield is derived empirically from satellite data. So what I do is I look within a given region, so say within a district, and I look at what are the maximum yields that farmers can actually achieve under the same biophysical, infrastructure, and political conditions. And typically what happens is when you use this as a yield potential value, the amount of yield gap that can actually be closed is a bit smaller, but I believe is more realistic. So to show how I applied this to northern India, I'll walk through a few different maps. So first what I did was I identified the magnitude of yield gaps across the Indo-Gangetic Plains. Once again, this is the main wheat growing belt in India. And I did this at the district scale. And what I did was I looked at the difference between the mean average yield within a given district compared to the maximum yield, which I defined as the yield at the 95th percentile of all possible yields within a given district. And when you do the analysis like this, you can see that the maximum yield gap is about 50%. And this is pretty different than what you see in the literature. So previous studies that have used the crop model simulation approach typically show that yield gaps are as big as 100%. So we're showing that they're much smaller in size. Second, what I'm able to do with satellite data is I can examine how much of that yield gap is actually explained by biophysical factors. So for example, weather variables or differences in soil type. And the reason I want to consider this is these biophysical factors are much more difficult for farmers to manage than, say, management practices. So what I wanted to do was remove the effect of these biophysical factors and then look at what yield gap remains, which is likely attributable to differences in management practices. And when I do this, we see that yield gap numbers are at most 30%. The other great thing about satellite data is that it allows me to examine fine-scale spatial variation in low versus high yields. And I just wanted to show two zoom-in maps to show some of the interesting things that we can see. So in this first panel, I'm showing yield differences between Haryana, which is a more prosperous state in the western part of the wheat belt, and Uttar Pradesh, which is a less prosperous state in the east. And the split between these two states is this river, which you can see right here in black. And what's striking is that in Haryana, you have right across the border, you have higher yields, which are represented by warmer colors. And right across the state line, you have lower yields represented by cooler colors in Uttar Pradesh. A second example of what satellite data can reveal is this is a zoom in of an area in Bihar, which is the easternmost state in this wheat belt, and it's typically the lowest yielding state. And what we find is that even though overall colors are mostly blue, representing low yields, there are some higher yielding patches that are almost as high yielding as places in the West. So what I wanted to do was try to understand what are the social, economic, and biophysical factors that can explain why we have such high spatial variation in yield within a small scale. So in order to do this, I compiled a variety of different data sets at the village scale across all of the IGP. That's 180,000 villages across this area. And I pulled data from census data sets on irrigation access and demographic factors. I'm not going to go into the details of what all of these variables are right now, but I would be more than happy to chat after the talk. I also pulled in information on crop management, specifically sow date, and this is something that I was able to derive using satellite image analysis. And then we also included biophysical factors like temperature, rainfall, soil type, and elevation. And I then ran random forest analyses to try to understand which variables explain the most amount of variation in yield across space. And what I found in the state of Punjab, this is that westernmost state, sow date is the most important factor. And when I do this analysis across all 4 states in the IGP, I interestingly find that sow date is either the most important or the second most important factor. So this suggests that this is one management strategy that might be able to be managed to close yield gaps in this area. And if you read the agronomy literature, this makes a lot of sense because of the way that wheat is negatively impacted by warming. So in India, most wheat is grown, or all wheat is grown in the winter season. Ideally, it's planted by November 1st because the winter season is pretty cool and wheat does well with cooler temperatures. But at the end of the growing season around March, there are a lot of hot temperatures and a lot of warming that starts to occur at the end of the growing season. And if farmers sow their wheat late, say in December or January, what happens is that warming period at the end of the growing season overlaps with this period of grain filling in wheat, which a lot of studies have shown is the most susceptible time for wheat to be impacted by warming temperatures. So this is a really mechanistic understanding of why sowing wheat earlier actually leads to big yield benefits. So the next thing I wanted to see was, do you get the same answer when using typically used district level statistics? So I did this in two ways. I aggregated my remote sensing estimates of yield to the district level, and I also used district census data sets. And when I do this, you can see that the importance of sow date drops down drastically. It now becomes a mid-range or low-range factor. And what this shows is that district level data, which is just often what we have access to when looking at these questions across large scales, it actually masks the importance of some variables that actually are very, very important for closing yield gaps. And these are factors that vary at various fine spatial resolutions. So the main findings from this work are that satellite data allow for more realistic estimates of yield gaps. Planting wheat earlier is one management strategy that can likely increase wheat yields and close existing yield gaps. And the importance of sow date is masked when using typically used district level statistics. So the implications of this project for my broader framework are that satellite data allow me to more realistically quantify how much changes in management can actually improve agricultural production because they allow me to account for real-world biophysical and management constraints. Satellite data also reveal important management strategies that just can't be detected with coarser level data. All right, now that we know that sowing earlier is one strategy that would be beneficial, what I wanted to understand is why are farmers not sowing early? Why do we even have farmers who are sowing late if you're getting such large yield penalties by planting wheat late? So in order to do this, so first what I did was I created a map of sow date across all of the IGP. Once again, this was derived using satellite data, specifically MODIS data. So this is at a 250 meter resolution across this area. And in warmer colors are areas that plant earlier, around November 1st. And in blue and cooler colors are regions that plant late as January 15th. And what you can see is that there's a lot of variation in sow date across this area, with farmers typically planting earlier in the west and planting later in the east. But at the same time, you do have areas where there is a lot of variation, where some farmers are planting early and some farmers are planting late. So what I'm doing is I'm collecting household survey data from 2,400 farmers across the IGP, and I'm asking them directly, what are your constraints to sowing? What are your sow dates? And what are some potential factors that might be influencing this decision? And specifically, I'm following these same farmers through time over 3 years to collect a panel data set, because that will allow me to better infer causality in my data and not just correlational analyses across space. So I can see how the same farmer makes different sow date decisions in different weather years. And this fieldwork is being led by a postdoc of mine, Sukhwinder Singh. He's here on your left, and he's interviewing a farmer here in the state of Punjab. So right now we're in the middle of data collection. This is part of a 3-year grant that I got from the NASA Land Cover and Land Use Change Program to look at how environmental change is impacting farmers. We've collected 2 years of data, and we're about to collect the third. But we have done one preliminary analysis in the state of Bihar to try to understand what are the factors influencing decision making. And the reason I focused on this area is this is one region that we see there is a lot of late wheat sowing already. In order to do this social science or this household survey work, I use a framework that I developed that examines the multiple cross-disciplinary factors that influence decision making, and I also quantify whether the decisions farmers are making are actually adaptive and beneficial considering yield. So there's a lot of previous literature on adaptation, and what I found through doing a literature review was that most previous studies, on average, only examine 2 of these different categories of factors looking at decision making, whereas a lot of work has shown that decision making is very complex and depends on a lot of different factors, so it's important to consider more of a holistic approach. And the second thing I found through a literature review was that fewer than 20% of papers actually look at the outcomes of the decision. So they'll often assume that if a farmer changes their behavior, it's an adaptive strategy, but I believe you can only call it adaptive if it actually leads to some sort of yield benefit than if they had not changed. So this is the approach that we take. So this was a paper that has been led by an undergraduate in my lab, Danielle Newport. She's currently a junior at University of Michigan, and we've just recently submitted this paper. And what we did was we wanted to ask farmers, what is your ideal sow date? And when we do this, we find that the majority of farmers say that the ideal sow date is between November 16th and December 1st. And this aligns with what agronomists in the region say. Usually agronomists will propose that farmers sow between November 15th and November 20th. But when you actually look at when farmers sow, many farmers are sowing later than that ideal window. So we wanted to understand what are the constraints to early sowing. Obviously, farmers understand that it's beneficial to plant early, but why aren't they? So we directly asked farmers, why are you not sowing during your ideal window? And we found that the most important factor that farmers said was that the rice crop was still standing. So as I mentioned, wheat is a winter crop, which is planted after the main monsoon growing season. And in this region, most farmers are planting rice during the monsoon season. So what this result is suggesting is that if farmers still have rice standing in the field, they're unable to plant wheat on time. They also said that lack of irrigation and waterlogging were also constraints. I then wanted to look at this question statistically by exploiting cross-sectional variation in early versus late sowing and try to understand what are the factors associated with those farmers who sow early versus sow late. And I don't want you to get bogged down by the regression table, so what I've done was highlighted in red what I think are the important findings. But what we see is that 2 main factors come out to be important. The first is what type of irrigation access farmers have. So what this result is showing is that farmers who use groundwater are more likely to plant wheat earlier than farmers who use surface water sources like canal. And this is likely because, from speaking with farmers on the ground, canal irrigation is much more insecure in this area. It's really dependent on the amount of rainfall in a given year and also how much of that resource is being used by other farmers, whereas with groundwater, farmers have much more control over the timing and the amount of irrigation. The second factor that comes out to be important isn't surprising based on the farmers' perceptual results. This is that if farmers plant rice during the monsoon season, they're more likely to sow wheat late. I then wanted to understand what are the characteristics of rice management that might lead to late wheat sowing. And this is because over 85% of farmers in this area sow rice. So having them switch to another crop in the monsoon season might not be a viable intervention. So when we did this analysis, this once again is just for the subset of farmers who plant rice. Once again, irrigation variables are important, but the second thing that comes out to be important is the sowing method of rice. So what we find is that if farmers transplant seedlings from nurseries into their fields, this is of rice, they're more likely to sow wheat later. The other alternative seeding approach is to direct seeds directly into the field and not deal with this issue of transplanting. And the likely reason for this is that if farmers are transplanting their rice, this typically leads to later rice establishment, and this has been shown in multiple regions across the world, including South and Southeast Asia. So maybe one potential interventions that we can get from this research is that promoting direct seeding of rice might be a viable strategy. I then wanted to look at what are the factors of those farmers who transplanted rice that might lead to late wheat sowing. And we find, not surprisingly, that those farmers who transplant their rice later also have late wheat sowing. So what this really highlights is that you need to take a systems approach to understanding decisions in the winter season. You can't just think of interventions for wheat. You really have to think of rice-wheat cropping systems together. I then did a scenario analysis just to understand, using the regression results, how much hypothetically could wheat sowing be brought earlier if farmers adopted direct seeding or if they were able to transplant early. So what I did here was I took my data table of all the farmers. I then in that data table replaced transplanting with direct seeding, and I also replaced what date they sowed their seed or transplanted their seed to be the earliest. And what I found was with each of these different strategies, so with the original data set, only 30% of farmers were able to sow before November 30th. So you can see many farmers are not sowing on time. When we do the quote unquote scenario intervention where farmers switch from canal irrigation to borewell irrigation, we find that only 31% of farmers sow wheat on time. So this really only improves 1% of sowing earlier. However, if we do interventions in the rice season, for example, getting farmers to transplant their rice early, all of a sudden 72% of farmers are sowing wheat during the ideal window. And according to our results, if farmers switch to direct seeding, they could sow their wheat even earlier. Around 88% of farmers could sow wheat on time. And I acknowledge that this is a scenario analysis and has its limitations, but I think that this does offer some insight into potential leverage points that might be more important than others. So the main findings of this particular study are that access to canal irrigation is associated with late wheat sowing, probably due to being more of an insecure irrigation access source. And second, most importantly, growing rice during the monsoon season, transplanting rice, and transplanting rice later are associated with later wheat sowing. And this suggests that we really need to take a systems approach to try to understand and identify ways to help farmers sow wheat earlier. Now what we're doing is we're in the midst of trying to understand how generalizable these findings are across space and also through time, given that we will have this temporal data set. So the implications of this work for my broader framework are that household survey data reveal important mechanisms that can inform policies to promote crop management decisions that actually increase production. And second, household survey data are critical to understand the drivers of that individual level decision making. So now the third project that I want to highlight is one that examines sustainable intensification strategies and looking at whether we can use satellite data to target interventions and measure the impact of interventions more effectively. So to do this work, I partnered with CIMMYT, the organization that I mentioned at the beginning of the talk, and we ran an experiment in real farmer fields. So we partnered with 150 farmers in the state of Bihar. This is that state in the most eastern part of the IGP. And we gave them access to a new fertilizer spreader technology that more evenly applies fertilizers. So we did a split plot experiment where in half of the plot, farmers applied fertilizers in the typical way, and then in the other half, they adopted the fertilizer spreader technology. And the reason we think this is beneficial is right now, the typical way of applying fertilizers is hand spreading fertilizers. And you can imagine that this would lead to a lot of inefficiencies because you might not have even application of fertilizer across the field. So CIMMYT developed this technology, which is basically a plastic backpack with a crank. And we put in the exact same amount of fertilizer. And then the farmer walked up and down his field, turning the crank, which probably led to more even application of fertilizer. And we wanted to see, does this more even application lead to increased yields without increasing inputs at all into the system due to increased nitrogen use efficiency? And this is a paper that we're going to be submitting to Science in the next week or two. So usually when impact evaluation of agricultural technologies is done in the field, typically the way that you collect yield data is by getting what is called crop cut data. This is the gold standard for measuring yield in the field. So what you'll do is you go out with the farmer during the time of harvest, and you'll harvest a given plot of wheat, say a 2 by 2 meter square. You'll then remove the grains from that wheat and weigh it in field. But you can imagine that collecting yield data in this way is really time and cost and labor intensive, which makes it really challenging to do at large spatial and temporal scales. And this has been a big limitation for doing large-scale impact evaluation of agricultural technologies in smallholder systems. So what I wanted to see is whether our algorithms to map yield from space and using these yield maps, whether this could be an effective way to pick up the impact of that intervention and do impact evaluation using a very low-cost measure of yield where you don't actually have to go into the field and do all of these laborious crop cuts. And I also wanted to see whether you could use satellite data to identify which fields would benefit most from the given technology, so we could potentially use satellite data as a way to target the intervention. So specifically for this project, I'm using very high resolution estimates of yield at about 2 to 4 meter resolution. So this is a yield map that I produced in the state of Bihar. Cooler colors represent lower yields, warmer colors represent higher yields. And the reason that I was really interested in using these high resolution data sets is because typically we'll often use NASA satellite data, which is readily available and a really great resource. But you can imagine, and as you can see in smallholder systems, they often do not allow us to actually get at field level yields. So what I'm doing for this project is partnering with a startup out in the Bay Area called Planet Labs. I've heard some of you are working with these data already, but they have created what are called doves, so little tiny satellites that are about the size of a shoebox, and they're shooting them up into space. And through these satellites, they're able to get high resolution data of about 4 meter resolution almost every day across the globe. So we're using these data to actually map field and subfield level yield of farms in India. So first I wanted to see, does our fertilizer spreader actually lead to yield gains? So this is using crop cut data that we collected in the field, and we find that yields increase by 4.5% on average. And once again, this is with absolutely no increase in input. This is just by using that backpack, which is only about a $20 cost, so a very low cost intervention. And 4.5% may seem like a small number, but if you'll remember from my earlier project where I tried to map yield gaps in this area, in reality, yield gaps can probably be closed by about 20% in this area, so 5% is a really big way or a big move towards that goal. I then wanted to see, can we pick up these yield gains? Can we see the benefit of the fertilizer spreader technology using satellite data? So in order to do this, we collected GPS field boundaries for the different subplots where we did the experiment on farmers' fields, and we lined that up with our yield maps that we produced using high-resolution data. And what we can see is that we are able to accurately estimate yield when compared to crop cut yield values, both at the plot and also the subplot level. And when I then ran that same analysis to see, can we pick up yield gains from space? The answer is yes. We were able to see that the fertilizer spreader technology led to increased yield gains just by using the satellite data. And this suggests that satellite data can be a great way to do low-cost impact evaluation in agricultural systems. The next thing I wanted to do was see whether there were any characteristics of farms that explain how successful the fertilizer technology is. So is there something that explains how well the technology will do? And to do this, I ran a regression, and the main factor that we found to be associated with the largest yield gains was the initial yield of the field. So basically, if the field was originally low yielding, if they then used that fertilizer spreader, they got the largest yield gains, both in terms of absolute yield gains and tons per hectare, and also percentage increase. And initial yield explained about 12 to 30% of that yield variation. I then thought, well, I wonder whether we can use satellite data to identify those fields that are lower yielding and then see whether those fields would be the ones that get the biggest yield gains. So what I did was I ran a regression where I looked at mean yield in the previous year prior to the experiment and then saw whether that was associated with yield gain. And what I find similarly is that those lower yielding fields, or the fields that have low production values, are the ones that benefit most from the spreader technology. Next, what I did was I ran a scenario or a simulation analysis to understand what additional yield gains could we get if instead of giving this technology out at random, we actually targeted the most lowest yielding fields across the eastern Indo-Gangetic plains. And when I do this analysis at scenarios of 5% adoption, 10% adoption, and 20% adoption, what we find is that yield gains can approximately be doubled if we can target those right farms using satellite data. Additionally, I did social surveys with the 150 farmers after the experiment that we did with them, and I asked them about their perceptions of the technology and how much they would be willing to pay for the technology. In this part of the experiment, we worked with the farmers and currently gave them the technology for free. And interestingly, what we found was these lower yielding farmers, these were the farmers who saw the most benefits, they also had higher willingness to pay for the technology. So this suggests, I didn't actually do an intervention where I looked at adoption and diffusion, but this does suggest that there might be some increased willingness to pay and potentially increased adoption in these targeted farmers. So the main findings are that the fertilizer spreader leads to large yield gains with no increases in input. These yield gains can be detected using satellite data. These yield gains are largest for those lowest yielding fields. And satellite data are able to target those lower yielding fields, and in our scenario analysis, suggest that we could double yield gains with the same intervention effort. So the broader implications of this work suggest that satellite data might provide a low-cost way to do impact evaluation, and satellite data could be used to target technologies to the places where they will do best. So this feeds into some future work that I am really excited to do over the next 5 years, and that is to actually run an experiment on the ground using a randomized controlled trial approach to see if whether you target farmers using the satellite data, whether that leads to increased adoption and diffusion of the technology across a given community. Because up until now, I just ran a simulation where I assumed 100% adoption of the farmers we targeted, but in reality, as you guys know, that isn't always the case. So we want to understand what would actual levels of adoption be. So there's a long literature on technology adoption and the adoption of interventions in agriculture. And much of this work examines the characteristics of farmers who adopt or do not adopt a new technology. And there's been a growing body of work that has started to focus on whether you can use this information to actually target interventions to the places where they will be most effective that might lead to increased adoption and diffusion within a given community. So as an example of this, there's been a lot of work looking at social networks and exploiting social networks as a way to give out technologies. So as an example, you would go into a village, map a social network, find who the most well-connected nodes are within a social network, and then target those technologies to those farmers. And studies have shown that if you're able to target in this way, you actually lead to increased adoption and diffusion of the technology within a given community. The downside of this approach is you can imagine it's challenging to go into a village and get some sort of social network data a priori. So what I argue is an alternate approach for targeting could be using satellite data to actually identify those farmers who would do best, give them the technology, and see whether that leads to increased adoption and diffusion through time. So this builds on my previous work by taking it from more of an observational or on-farm experimental approach to actually an intervention and policy rollout experiment. The second broad avenue of research that I'd like to pursue over the next 5 years is collecting long-term panel household survey data to more causally identify how farmers change their behaviors in response to change. So unlike agricultural production data, data on decision-making and household characteristics are often very challenging to find in high temporal frequency where you follow the same farmer through time. But I believe that having such data would be really beneficial because you could follow the same farmer through time and see how their decision-making changes in different weather years based on interannual rainfall variability. And if you collect data over a long enough time period, you might be able to see how farmers in one region that may have faced some long-term trend have different decisions than farmers in another region that didn't have the same long-term trend. So this is just an example of two potential cases. So in black is the adoption of earlier sowing through time. In red and in orange are warming temperatures and groundwater depletion. And in this case, you could maybe see that possibly farmers are shifting to earlier sow date because of these long-term environmental changes, but that would only be a correlational association. It wouldn't be causal. So what we could try to do is exploit this interannual variation in groundwater depletion and weather variability to see whether that's associated with interannual variation in decision making. So in order to do this, I propose to continuously collect annual panel data that follows farmers through time for at least 10 years. Through my current work, I'll have at least 3 years worth of data, and I propose to collect this data even longer moving into the future. And finally, some ongoing work that I want to highlight. Today, I only presented work that I'm doing right now in India, but through collaborations, I'm starting to take this model and framework and apply it to other regions in the globe. And I would be happy to speak with anyone about that after this talk. But specifically, I'm partnering with others to look at irrigation decision-making and changes in irrigation decision-making in the US, and also the adoption of cover crops as a sustainable intensification strategy in the Midwest. So I'd like to thank the various collaborators that have been a part of the various projects that I mentioned today. With David Lobel and George Azari. David Lobel is an agricultural ecologist and remote sensor, and George Azari is a remote sensor at Stanford University. We've been doing a lot of the yield mapping work together. With Ruth DeFries, Jillian Galford, and Pinky Mondal, who are all geographers, we've been doing a lot of the cropped area mapping work. With Shahid Naeem, who's an ecologist, we've been looking at what are some of the environmental impacts or outcomes of adaptation decisions, and I didn't get a chance to present that work today. With Manu Lal, who's a hydrologist, and Ram Fishman, who's an economist, we're looking at the impacts of groundwater depletion on agricultural decision-making in India. And with Benjamin Orlov, who's an anthropologist, we're looking at ways to think about adaptation within the social sciences. And then finally, I'm collaborating with Arun Agrawal, who's a political scientist, to think of interventions that we might be able to roll out in India to increase food security. I'd also like to thank the researchers at CISA CIMMYT, who I've been working with very closely on this warming work, particularly Balwinder Singh and Amit Srivastava. And then I'd also like to thank the students in my lab who really contributed a lot to this work as well. Great, and then I would also like to thank my various funding sources. Great, thanks so much.
Questions from, because that way no one can get upset with me later. But just to bear in mind, there are microphones, so when you put up your hand, if you get it, just wait 1 minute and we'll grab the microphone.
Great, thanks. Go ahead.
Hi, I had a question about the switch from transplanting rice to direct seeding and how that could potentially impact rice yields, because you might expect direct seeding could be associated with poor germination. And would that then sort of, what would be the balance between, increased yields due to the two different crops or lower yields?
Yeah, I think that's a fantastic question, and that's something that I'm partnering with CIMMYT to better understand. So they've been actually running a lot of long-term agricultural trials where they look at the impacts of adopting this technology on yields. And we're still in the middle of that work, so I don't have a good answer, but all I can say is we definitely are considering that. And I'm never going to try to promote a strategy that isn't actually going to be beneficial for farmers on the ground. But I would imagine that's one constraint to why many farmers aren't already using direct seeding in the area. Yeah.
Really appreciated the talk. Thank you so much for coming. With the panel data, I'm wondering how you're thinking about the potential effects of the interviews on farmer behavior and whether there's anything you need to do to prevent that from influencing people's decisions.
Yeah, that's a great question. So the way that we design our surveys is we try to make them as observational and not leading as possible. So when I was collecting that information about sow date, I was actually just getting plot-wise data on the practices farmers were doing, and I wasn't asking them questions like, why aren't you sowing on time? That would obviously lead to yield benefits. I try not to lead it in any way whatsoever. And one way to do that and make sure that we do that appropriately is before we design any sort of large-scale structured survey, I actually do focus groups, or my lab does focus groups in the community to really understand the local context and make sure that the questions that we're asking are locally appropriate and also not leading.
Thank you for a fantastic talk. My question is about satellite application in yield monitoring. As you know, the satellites actually, they don't measure yield. They measure some proxies of yield, maybe greenness, so, or as you point out, the phenology of the crop. I wonder how you translate those proxies to the actual yield. And another related question is, at what spatial scale your approach is most reliable?
Yeah, those are two great questions. So for the first question, I'm taking two different approaches. So at the more local level, where I really want to get individual field level estimates, the approach that I'm taking is just a regression approach. So what I do is I have crop cut data, which are real on-the-ground measures of yield that I use as calibration data. And I use that as the input into a regression with vegetation indices or measures of greenness and biomass from space. And through that, we're able to come up with really accurate estimates of yield. That, of course, is very challenging to do at very large spatial and temporal scales because you probably won't have access to this rich crop cut data across all of northern India. So in order to create those yield maps, I actually used a different approach called the Scalable Crop Yield Mapper, and this was developed by David Lobel at Stanford University. And what we do there is we actually don't use any ground data for calibration of the model. Instead, we run crop model simulations where we simulate what we think vegetation indices would look like based on realistic management factors on the ground. And then we use those simulated VIs to estimate, to come up with a linear regression that we can then apply to real remote sensing vegetation indices. So in terms of accuracy, I would say that the models that are strictly regression-based, where we regress them on crop cut data, those are definitely much more accurate, especially if you do them at local scales. But I would say that it's not possible over large scales, and this other skim approach is really a viable way to get pretty accurate estimates at large spatial and temporal scales. Did that answer your questions? Yeah. Great.
Thanks for a really interesting presentation. I especially loved the maps where you could see the stark contrast between the political boundaries. I'm wondering if for some of these strategies, is there a trade-off between yield and risk? And maybe some of the differences in farmer behavior are driven by which farmers are able to better manage risk. For example, wealthier farmers could better insulate themselves, so adopt more high yield, high risk strategies.
Yeah, that's a great question. So in our models where we're looking at what are the factors influencing decision making, we also do include some factors that are correlated with people's risk-taking behavior. And we've actually found that to often be a big explanatory factor for the decisions farmers are making. So I'm not going to talk about this specific study, but I did some other work in the state of Gujarat in northwest India where I looked at how farmers were adapting to a delayed monsoon onset. And the most risky strategy in that case was to continue to plant rice and cotton, which were the typical cash crops in a given region. And the only people who continued to adopt that risky strategy during late rainfall years were the rich and the more risk-taking farmers. So I definitely think that that plays a big role, and I'm hoping that by collecting these broad sets of data, I can get at that, but also by collecting the data through time, I can look at which strategies might be beneficial just in 1 year versus strategies that might be beneficial across time.
Thank you. I was wondering if you could elaborate how you and your lab chose the farmers that you were going to interview, if there's like certain factors that were involved, and what are the plans to like keep in touch with them for such a long period of time, and how often do you have to interview, and some of those types of questions.
Yeah, that's a great question. So the way that we find our farmers is First, I'll pick the villages based on looking at remote sensing maps to make sure I'm getting variation in the variable I'm interested in. Then we'll go into the village and we'll actually speak with the local village head, which is the equivalent of a mayor of a small town. And we'll ask them first if we can interview in their community, and if so, if they could give us an idea of the representation of people within their community across castes and also landholding size. And then what we'll do is we'll use a random but stratified sampling approach where we'll go around the village and interview people in their homes, but we'll make sure that the data are representative of that broader caste and landholding size distribution that we got from the village head, just to make sure that the people we're interviewing are representative. We don't take a full random approach, which would involve, say, getting a roster of all the villagers in the field and then picking people at random and going to them, just because we found that that's really time intensive and challenging to do in the field because these rosters often don't exist at the local level. And we feel like our approach is sort of a good mix between trying to be stratified but also being a bit random. And then in terms of keeping in touch with the farmers, we've been going back every single year, and we have addresses and GPS points for the farmers and also their phone numbers. And so far, every farmer that we've met has been willing and happy to do the survey again, but we do have attrition because some farmers do move out and whatever else.
Let's have one more question.
Thank you very much for that awesome presentation. I'm wondering if the Lobo Lab is developing other scalable crop yield models. I know that they have one for wheat and soy, but are they developing one for rice? And would there be any potential limitations that you could think of that?
Yeah, so from what I know right now, they're not working on rice. They are working on maize, and hopefully they're going to have, I think it's okay if I say this, hopefully they're going to have global maize maps sometime in the upcoming future. I think we've shied away from doing rice because that's a crop that's typically planted during the wet growing season in a lot of the world, and that makes it really challenging to actually get accurate vegetation indices because there's so much cloud cover. So we're thinking about moving to that crop, but we would probably have to involve other data sets like radar data sets, which we just haven't looked at yet.
Okay, we're going to need a break, right? So I want to thank, actually I want to thank the question askers for asking concise, pointed questions. It's always great because we get a lot of questions in. I want to thank Meha for, hopefully what you got out of that talk, one thing I got out of that talk is just a huge amount of data and effort that goes into making any one of those papers. And one paper is not equal to another paper, right? They can differ very much in terms of how robust the underlying information is, and so it's fascinating to see kind of the work behind each one. So thank you for coming.
They're awesome.
We're going to get, Karen's going to take you into the doctoral students.
That sounds great. Thank you.
You've got to walk out that way when you're doing it.
Okay, sounds good.
So
So before it actually happening, when it restarts, we'll be able to actually
Where? All right, let's restart it. So I have there's two inputs on the back here, right?
Yeah.
There's DisplayPort and then there's the DVI. The DVI is the HDMI to DVI so the HDMI to DVI is coming off of the switcher, so it's showing the exact output that's showing. So the Mac is only seeing one display connected. The other one comes off as a secondary display into DisplayPort. So if you hit input, you can switch between the two. I didn't do that. NSLC did that over the summer when they went and rearranged things in there. I kind of thought it might be a good idea if we wanted to keep presenter view, so you could switch back and forth. Maybe that's not the case. So
when you can do one or the other, it wouldn't split. And now you're seeing times. Is there a presenter view there? Or like, can you log in?
no.
There we go.
So this is showing the secondary display.
I would keep that for a second. See if it go back to where you were.
Okay.
Now pop open a PDF or not PDF, PowerPoint. There we go. Perfect. That's why I would say keep it where it is now, because we can log in and it actually doing what it's supposed to.
Okay.
One thing I haven't listened to any other recording lately, but the ones I listened to was really hot audio wise, so we should check in.